day. And myself, Dr. Suparna Vishwas, Associate Professor in the Department of Computer Science and Engineering, and Dr. Sriporna Saha from Computer Science and Engineering. On behalf of the organizing committee, welcoming you, sir. And thank you very much. We express our sincere thanks to accept our invitation within very short period of time and joining us. So over to you, Dr. Sriporna.
Okay, so I'm going to introduce that. So Dr. Swagatam Das received D in Telecommunication Engineering, ME in Telecommunication Engineering with Control Engineering specialization and PhD degrees all from Jadavpur University, India in 2003, 2005 and 2009 respectively. Swagatam Das is currently serving as an associate professor at the Electronics and Communication Sciences Unit of the Indian Statistical Institute, Kolkata, India. His research interests include evolutionary computing, pattern recognition, multi-agent systems, and wireless communication. Dr. Das has published more than 300 research articles in peer-reviewed journals and international conferences. He is the founding co-editor in chief of Swarm and Evolutionary Computation, an international journal from Elsevier. He has also served as the associate editors of the Pattern Recognition Elsevier, Neurocomputing Elsevier, Information Sciences Elsevier, IEEE Transactions on Systems, Man and Cybernetics, IEEE Computational Intelligence Magazine, IEEE Access, and so on. He is an editorial board member of Progress in Artificial Intelligence Springer, Applied Soft Computing Elsevier, Engineering Applications of Artificial Intelligence Elsevier, and Artificial Intelligence Review Springer. Dr. Das has 20,500 plus Google Scholar citations and an H index of 67 till date. He has been associated with the international program committees and organizing committees of several regular international conferences, including IEEE CEC, IEEE SSCI, SEAL, GECCO, and SEMCO. He has acted as guest editors for special issues in journals like IEEE Transactions on Evolutionary Computation, IEEE Transactions on SMC, Part C. He is the recipient of the 2012 Young Engineer Award from the Indian National Academy of Engineering INAE. He is also the recipient of the 2015 Thomas Reuters Research Excellence India Citation Award as the highest cited researcher from India in engineering and computer science category between 2010 to 2014. And today our talk will be delivered by Dr. Swagatam Das on deep generative adversarial networks and some. So over to you, sir, for your
Thank you, Sriporna. One second, just have an announcement. Professor Devashish Dev, Professor of Department of CSE and also Director of Computational Science, has joined us. So, sir, if you say few words to welcome Dr. Swagatam Das. Professor Dev.
Devashish Dev, sir, please unmute your mic, sir. Yes, sir.
Professor Dev, can you hear me? Hello. Maybe some audio problem or sure. Same, I think his link, there may be some link problem or maybe
Yes,
we
network
can,
issue. It is network
yeah,
issue.
we can hear from him
Yes,
after
yes,
the talk also.
Devashish Dev, sir, can join, sir. Sir, please unmute your mic, sir. Devashish, sir. Devasi sir, please. Yes, sir, we can hear you, please, sir.
I think some audio issues.
Yes.
Okay, so we can move on to, and we can hear from him after the talk as well, I think. So, Dr. Shavatam Das, so please over to you, sir. And coming time, we are waiting to hear you. Over to you, sir.
Thank you, Dr. Vishwas and Dr. Shaha. I will have a time. What is the time for the talk? Let's see. Let's say 45 minutes to 1 hour.
Have time. The slot is till 4, but at 2:30 we have valedictory, as I have informed you. So it's up to you. Like
Yeah, okay.
it's up to
So
you.
I will try to be between sometimes between 1 hour and 15 minutes and 1 hour and 30 minutes, something between that.
Okay.
So thank you for this invitation, and I'm glad to see my old colleague Professor Devashish Dev is also here. So I will start with a presentation and share my screen. If you cannot hear me at any point of time, or there is some audiovisual issues, please let me know.
Yes, sure.
Okay.
Sure.
So yeah, now let me share the screen. So I hope you can see the screen. And
Yes, sir, visible.
so deep learning, this term has become almost a household term these days, instead of confining it to a mere research jargon. And most of the young researchers in computer science, in empirical sciences, must have heard of it. Even statisticians are all familiar with this sort of thing. Inside the realm of deep learning, one very important and state-of-the-art paradigm is this deep generative adversarial networks, or GANs. So this talk will focus on various facets of GANs and their applications to class imbalanced learning. The most important part of this opening slide is my email ID, which is given here. So if you face any question you want to discuss with me offline, or you require any kind of references, do not hesitate to drop me an email at this ID. So I begin with almost a zero background on machine learning and then develop towards this particular area. The supervised machine learning framework can be expressed very nicely with a very simple mathematical equation, y equal to fx. Before I go into it, what is machine learning? What is learning? Learning is a process by which we can take future decisions based on our past experience. That experience must be provided by some other human expert or teacher. For example, when I used to be a kid, my mother used to point to kids' storybook and say, look, this is a cat, this is a dog, this is a rat, etc. After a few rounds of such training, when I go on road with my mother and a little creature passes by me wagging his tail, I would yell out, mother, look, that's a dog. Excited. Somehow the gross texture, color, shape of that creature was registered in my brain, in my neural circuit, under the tag of dog. Although that dog was not the exact one printed in my book. So what did I do? Based on the experience provided to me by my mother, I took a decision about the category of that animal which passed by me. This is a typical example of supervised learning. Supervision is like teaching, is like giving the right experience, giving the right direction. It comes from a teacher, comes from a supervisor. Now I want to do the same thing. I want to make a machine do the same thing. In this context, machine is essentially a computer which understands nothing more than numbers, and better I say binary numbers. Okay? So machine learning, a machine learning system is essentially this F, this function of capital X, which is a vector of numbers which abstract some object, which provides the abstract measurements dealt on some physical object to a human being we have also 5 sensory organs, and these organs also actually abstract the different objects that we perceive. Now, for a computer, each object must be converted into an array of numbers or a matrix of numbers, which basically characterize that particular object. That is the feature vector or feature matrix or the feature tensor, whatever we call it. Features are the characteristic traits expressed in terms of numbers, and these numbers must be provided to a function f, which takes these numbers and returns some other number which denotes the correct category or correct class of the object, which is summarized in the vector or in the matrix capital X. That is the supervised machine learning framework. So how this function is made? The function is made through a training set. What is this training set? It is a labeled set of examples, labeled set of each bold xi is basically the feature vector. Let's call it vector for now. It's a feature vector of some object. Feature vector means array of numbers. Each number is a characteristic trait of the object. And then there is a y. What is this y? This y is the corresponding category of the object. Who said it is the correct category? Some human expert. So we have, suppose, digital breast mammogram images, breast tissue images by mammography. And there is an oncologist, there is a cancer specialist, a doctor who is an expert. So the doctor will label some of these images, suppose 100 of such images, into 2 classes. The doctor will examine these breast mammograms to see if there are off-white patches in some of these images, which are called microcalcification spots. If these spots are there, that's a strong indication of starting of breast cancer. So the doctor will say, okay, these images are malignant images and those images are benign images. 100 such images will be manually stamped by an oncologist whose time is very expensive. After we get these 100 stamped images, labeled images, we call it training set. Now we will use some algorithms, procedures, methodologies from machine learning, which will create a function like this, and the function will take these images and tell us, the function will be built up on this labeled set of images, and when a new image comes from an unseen patient at the outdoor of a very crowded hospital where no oncologist can manage that crowd, so when the unseen patient's mammogram comes, we will rely on the computer, which will tell us whether this patient should be categorized into malignant class or benign class. Based on that, the treatment will be initiated, right? So this is just an example of usage of supervised learning also in computer-aided diagnostic systems. Okay. So given the features of an image, each image is also an object, maybe the image of an object, and you just abstract that image in the form of some numbers which create a vector. These numbers might be the simple, pixel values from the image. So when such images are passed into the function, this function itself is a machine learning system. We call it prediction function. Statisticians are very good at giving very dry names. So statisticians call them models. I don't know why. So statistical models or prediction functions or classifiers, all are same. So these functions will accept features of these images and it will say which one is apple, which one is tomato, which one is cow, etc. Is it really so hard? The answer is yes, because human perception is a remarkable thing. No one knows how exactly human beings perceive different objects, demarcate one object from another. When we look at a motorcycle like this, we immediately perceive the handles, wheels, etc. We do not, when some of you look at the face of your friend, do you look at it like the top left corner pixel is 223, beside that 156, beside that 124? Never. You look at the face and you immediately capture the high-level features, abstract and high-level features. What are these abstract and high-level features? Like white forehead, cut mark on chin, nice beard, etc. So human perception is something at very high level and very abstract level. So when we look at it, we immediately say, oh, it's a motorcycle. But when the machine looks at it, When a camera looks at it, what does the camera record? The camera records a digital image. The digital image is nothing but a two-dimensional array of piles of numbers. If it's a color image, there will be 3 such two-dimensional arrays in red, green, blue space or HSV space. There are different color models. So from these arrays of numbers, it is very difficult to infer something about the actual, category of this, what is being seen. These numbers, these pixel values, raw pixel values recorded by a sensing equipment. By the way, this talk will mainly focus on images. So there are texts, there are speeches, multiple such things are there, but I will mostly focus on images, which is most well known to many of us. So when we look at these arrays of numbers, these are like lowest level features which are close to the machine. They are just like the .exe code, .executable code, which is created by the computer from your .c high-level programming language code, a C code, let's say for example. The C code high-level programming language code is close to human being. The executable code is close to machines. Human beings cannot understand. Similarly, these pixel level features, which are lowest level features, are close to machines. Difficult to build up human-like interpretation from there. Just let's see an example. I mount a camera on the doorway of my garage, suppose. And the camera must distinguish between cars from non-cars. I don't want an elephant to walk into my garage or a bison to walk into my garage. Please. So if I just take 2 pixels, one from here and one from here, and plot the values of these 2 pixels along X and Y axis, I represent each image as a dot in this 2-dimensional space. Cars and non-cars, both the images will have these 2 pixel values very similar to each other or uncorrelated. There is no direct pattern. So what will happen? Cars and non-cars, both types of dots will become mixed up here. It will become a khichdi, and it will be very difficult to put a line of demarcation, a Lakshman Rekha, to demarcate points from one class from points from the other class. Instead, if we would have done something a little cleverer, I could have put a small 3x3 window with proper coefficients, 9 coefficients inside, which we call convolutional coefficients, which are so cleverly tuned that as soon as I drag this 3x3 window over the image, drag it in rows, the next rows, the next rows. If I drag it over the image, as soon as this 3x3 window captures a pair of handles, it would record a very high response. It would fire. So we call it handle detector. It's a very common principle in convolutional neural nets. Similarly, if I have another window which, as soon as it detects a wheel, it records a very high level response, high number. It returns a high number, 10, 20, something like that. If it doesn't record a wheel in the image, it gives us a very slow number, 0.001, something like that. So if I use these 2 feature detectors, and my objective is just to demarcate cars from non-cars, it's a 2-class classification problem. And I plot the response of the handle detector and the wheel detector along my X and my Y axis, what would happen? Cars will have a very high response for both. That's why the car points will accumulate here. On the other hand, non-cars, like a bison walking into my garage or an elephant, hippopotamus, for them, no handle, no wheel. So they will just have very small numbers and they will accumulate near the origin. And I will be able to demarcate by drawing even a straight line between these two dense patch of points. Right? So better feature representation is one of the most crucial things. Not only better, how to find abstract and high-level features from lowest level features. That is one of the major tasks in machine learning these days. It has remained as a major task for the last so many years. And it is not easy. Human beings are remarkably good at it. Even in 2-class classification problems, if you look at these pictures, sheepdog or mob, human beings can look at them and easily characterize which one is a mob. Mob will not have this nose-like and this tongue-like structure. This must be a sheepdog. That must be a mob. Okay. Similarly, puppy or beggar. Human beings, not only we immediately by our visual perception, not only we do the classification, but we also identify the features based on which we are classifying. Okay? Between the puppy and the beggar, between the barn owl and the apple. If I ask you, what is the feature based on which you are classifying? You say, okay, the distance between the eyes of the owl is much greater than the seeds of the apple. There is a nose-like structure for the owl. No such structure for the apple. The apple has a ridge-like structure at the out end of the tongue. Chihuahua or muffin, dog puppy or muffin, multiple muffin, multiple dog puppies. So you'll say, okay, the cherries are not regularly arranged in a muffin, but the eyes and the nose are arranged on the vertices of a regular triangle, almost regular triangle for a dog puppy. So this is how you distinguish. Try to make it by a computer. If we try to do the same thing by a computer, we will require machine learning, research, lots of Python programming, and blah, blah, blah. This is the engineering by the God. So obviously, anyway, so the point is, lot of the learning task by a computer depends on proper representation of each object in terms of proper features or proper numbers. Deep learning saves us a lot of effort in this context. It's also, so deep learning is nothing magical. It's just like a straw that the modern crow would use to suck up the water. Instead of putting stones and waiting when the water level comes up, deep learning is just like a straw. Okay? Let's look at it, how it works. The traditional machine learning includes a human expert here who will do all the feature extraction. Feature extraction means who will, from the lowest level features, who will decide how to combine these features in various ways to generate abstract high-level features to capture the main emphasizing facets of the object. Then the high-level features will be provided to a classifier or machine learning system, which will decide the correct category of the object. Deep learning attempts to eliminate the need for this human feature engineer. Previously, last 25 years of research in computer vision has seen lots of effort by separate human scientist groups who have came up with lots of feature extraction techniques like histogram of oriented gradient, scale invariant feature transform, text storms, etc. But each of them hold for a specific kind of images. Given and completely unseen image, what type of feature extraction technique would be best fit for it? Nobody knows. Deep learning saves us from that effort. Every deep learning system is a system of multiple feed-forward connected, simpler layers of mathematical systems for doing certain mathematical processes, and output of one layer forms the input of the next layer. Through this cascaded system, the information flows, each feature flows like a signal, and then the features are twisted, tweaked, combined in linear and nonlinear fashion to finally generate the most important, most discriminative, abstract, and high-level features. The final classification is done near the last layers of the deep neural network. So this is the biggest selling point, that the feature extraction part is taken care of by the system itself of deep learning. There are two deep inference models. One is called the predictive or discriminative learning model, which is happy in just predicting which object comes from which class. And these models are there for a long time. So the predictive model learns a decision boundary between the two classes of points. It learns that Lakshman Rekha, which demarcates between the two classes of points. Apart from that, we also have the generative model, which is the most important facet nowadays, which is also the central theme of this talk. The generative model is not only happy in learning the decision boundary, it learns the spatial probability distribution of the objects coming from different classes. Okay? It learns tries to approximate the underlying distribution, probability distribution of the objects. What does it mean? This is an age-old problem in statistics. I give you 5 numbers. 5 scalar numbers, 5.1, 2.6, minus 3.7, etc. And I tell you, give me a Gaussian distribution, give me a normal distribution from which these 5 numbers are most likely to be sampled. Statisticians have been after this problem since last more than 100 years probably. And one such mechanism is the maximum likelihood estimation, MLE. Okay. When there is some hidden variable in the scenario, we go for expectation maximization. But instead of giving you 5 scalar numbers, if I give you 5 multivariate observations, that means 5 big vectors, each vector is representing an image. And I ask you, now you estimate the underlying multivariate probability distribution, it becomes tremendously tough. Most classical algorithms fail to do it. Deep generative models try to estimate such underlying probability distribution. This is a density estimation problem, basically. Try to estimate the density, estimate the spatial distribution with the help of neural networks. That's the basic idea. To a normal human being, everything comes from nature or from God, or that's it. For a statistician, every object is a matter of chance, and it has been sampled from an underlying multivariate distribution, multivariate mixture of Gaussians or something like that. If you can have a hold, if you have a grip on that distribution, you become like God. So now you can, you can sample that distribution and generate new objects, which are very realistic, but which never existed. You generated it. That is the idea of generative networks. Once it gets sold, so this is the pictorial representation. The discriminative model or the predictive deep inference model can learn this decision boundary between the 2 classes. And based on whether the point comes from the left side or the right side of this decision boundary, the discriminative model actually gives us an estimate. Gives us the classification, the proper class. On the other hand, generative model learns the underlying probability distribution of the data, and based on where the distributions have minimal overlap, etc., which decides the class. Classification is a secondary task for them. Their main task is to understand this underlying probability distribution. Once it does so, it can generate fake images for image data. Once it knows that it can estimate the underlying distribution, it can generate lots of very realistic but fake images by sampling that distribution. Okay, that is the good side and also the bad side of generative networks. I'll come to it and show some results. So what are deep neural networks in a nutshell? 1980s neural networks used to have only one hidden layer. After 2012, everything changed. After 2012, most of the neural network had lots of hidden layers. These hidden layers are basically and a neural network is basically comprising of multiple such computing nodes which can process the input the flowing signals and route them to the output going links. These links are like signal carriers, and in the input layer, basically people connect the lowest level features, each feature for each node, one node. These features are like signals. The signals, while flowing through these links, each link has a weight. So these weights multiply the signals and cause them to attenuate or to amplify. Okay. Then there are various combinations of these signals, which is basically done by these hidden layers. So the hidden layers function, exactly how they function, the mathematical theory is still not fully developed. But people conjecture that the hidden layers combine the lowest level features like the pixels to form edges. Edges are combined further to form different parts, body parts. Body parts are combined to form, for a face database, obviously. For other databases, other things will follow. So the body parts will combine to form the most important abstract features, ear, eyes, nose, eyebrows, etc. And finally, these abstract features are combined to form the prototypes of each class. So when a new face comes, That new face will be matched against one of these prototypes for each class. And based on that, the inference, the categorization inference will be drawn. So this is the, so hidden layers are the main component of neural network. This was identified after a very successful application of deep neural convolutional network for a huge large-scale image classification. So this was the breakthrough. This was a breakthrough in 2012. This number is very old. This paper now has 70,000 plus citations, just in 8 years. Think of it. So Geoffrey Everest Hinton, one of the godfathers of deep neural networks, one of the key architects, along with his two students, used this deep convolutional neural network to classify a huge image database called ImageNet, which comprises of 1.5 million tiny images distributed over 100,000 plus classes. And before this paper, the average accuracy of the best known classical classifiers like support vector machines, naive Bayesian, DC, random forest, etc., was around 70%. This particular paper raised up the accuracy to 84%, and the error was 16%. The network proposed in this paper later on emerged into AlexNet, which was the prototype convolutional net in MATLAB 2017 and onward versions. So this picture shows you the revolution of depth. Depth means how many hidden layers are there in your neural network system. Hidden layers are the layers sandwiched between the input and the output. So as you can see, in 2015, the residual network came into picture, which had 152 hidden layers. By that time, lots of GPU-based processing technologies were available. This multi-core parallel processing improved a lot. As a result of that, we could afford 152-layer neural networks, and that gave us an accuracy of 3.5%. Sorry, error of 3.5%, accuracy of 96.5%, which is very close to human level accuracy. As human beings, when you are being shown images at a rapid succession, maybe out of 100 images, 2-3 images, you will mess up. For the others, you can clearly tell the categories. Okay, this is a bird, that's a cat, that's a tree, that's a coffee mug. You can rapidly say the categorization. So ResNet, residual net, was approaching human level accuracy. Now the accuracy, best accuracy in ImageNet is of the order of 99%. 2015 is 5 years back. In deep learning era, 5 years means 5 yugas. So lots of things have changed by now. Anyway, this 2012 paper was the beginning. After that, everything had seen a sea change. Convolutional neural net, this is very important for understanding what I'm going to tell next. And what happens inside the convolutional net? Convolutional neural networks accept images as their input. You don't have to pack up the image. If you have suppose a 16 cross 16 image, you have 16 pixels along the width, 16 pixels along the length, so 256 pixels in total. Regular neural networks require you to pack up this 256 pixels in the form of a 256 dimensional vector. That's okay for a 16 cross 16 pixel image. But if you have, nowadays every one of us have megapixel cameras. So if you have a 9 megapixel camera, you have 3000 pixels along this direction, 3000 pixels along that direction. So you have 9 million pixels. So that packs up into a 9 million dimensional vector. It's not easy, a 9 million dimensional array. 9 lakh entries inside there. Sorry, 90 lakh. 3000 into 3000, 9 into 10 power 6. So many numbers together, very difficult to adjust. That's why convolutional neural networks provide a way to accept images as two-dimensional array. They perform two operations to compress the image and also extract the high-level abstract features from the image. These two operations are convolution with nonlinearity activation, like ReLU activation, followed by max pooling. or average pooling, some kind of pooling which is a downsampling operation. So convolution and max pooling, basically repeated application of these operations on the image, compresses it in the form of tiny feature maps. These feature maps are also very small images-like structures, but they contain only high-level combination of the pixel-level features into high-level abstract features, nonlinear combinations. These feature maps are next packed in the form of a vector. This vector for a 9 million pixel image, 9 megapixel image, this vector may be just 2000 or 3000 dimensional vectors. Instead of handling a 9 million dimensional array, it's much better to handle a 3000 dimensional vector. So this vector comprises of the abstract high-level description of the image. This vector is fed into a neural network, fully connected neural network, which performs the actual classification. So if you look at convolutional net as a black box, the image is going in, and a vector, a much lower dimensional vector, comprising of the abstract and high-level features of the image, is coming out as the output. That vector is used as in the form of feature vector for subsequent classification. And the beauty is there is a single loss at the output. This loss, by calculating the gradients of this loss and back propagating the gradient, even we determine what should be the coefficients of these convolutional filters used inside, because the convolutional filters act as the major feature detector, and they are the key things to eliminate all the other redundant features. For example, if my objective is to distinguish birds from non-birds, what should I do? Why should I look at this huge background containing no useful information? I will only look at this beak, whether this picture has a creature with a sharp beak and feathers. These two are my matter of concern. I should not look at any other thing. I should not take care of all the 3000 and by 3000 pixels. That's what convolution filters do actually. This mechanism requires another talk of 3 hours, so I'm not going into that. But remember, convolutional net, input is an image, output is a vector comprising of high-level description of the image. What happens if we reverse the flow of a convolutional neural net? If we reverse the flow, that means then we provide a vector to the convolutional net as input, and the output is an image. So from the small dimensional vector, low dimensional vector, this deconvolutional network, this is called a deconvolutional network in reverse flow, it can generate a two-dimensional image. Do you understand? This would be a very important stakeholder in my subsequent description of GANs. So now there comes generative adversarial network, or GAN, which was a 2014 breakthrough. And the first paper appeared in the NeurIPS conference. Now it's called NeurIPS, at the time it's called NIPS. NIPS is the biggest machine learning conference of this era, along with ICML and AAAI. So in NIPS 2014, this paper was published. The first author at that time, he was a nearly 27 years PhD student, Ian Goodfellow. Now he's a superstar in machine learning. Now, Machine Learning Institute called MILA, headed by Yoshua Bengio, who is one of the academic children of Geoffrey Hinton. And this network first showed a very nice way of putting forth the generative models. As remarked by Ian LeCun, Ian LeCun is basically known as the pioneering developer of convolutional neural networks. So Ian LeCun, who is the director of AI research at Facebook, he said this is the most interesting idea in the last 10 years in machine learning. And Bengio remarked it's the future of artificial intelligence. So GANs, if you show it, this is a machine learning system. If you show it multiple images of a specific kind, like multiple bedroom images with different linens, different cots, different windows, etc. So GAN can itself generate new bedroom images, which will look exactly like a realistic bedroom, but which were never created on Earth. really. So GAN was, trained with lots of, so GAN was trained with lots of medieval period portrait images, and thereafter GAN created its own medieval period portrait image, which is shown here, and there is a signature here. The signature reads generative adversarial network. This image in 2018, it was auctioned. This image was auctioned in USA for $432,500 US. So it can create such things. Okay? Let's see how it does. So let's try to understand. It's not very easy to understand it, especially in a limited time lecture, but let me try to give you a feel of how it does. Okay? As I told, this is an age-old problem in probability and statistics, but now it is being solved very remarkably for very complex scenarios by probabilistic generative models accept real observations from real world, and the model provides synthetic observation. Observation is a nickname for these feature vectors coming from real world objects. And the goal of modeling is to match these two as closely as possible. So the density estimation is basically probability distribution of the observations from real world must match probability distribution of the synthetic observations coming from your model. Like all other numerical analysis tools and techniques, what do you do in numerical analysis when you try to solve a particular problem? You start with a trial solution, a very easy gauged solution. Then as time proceeds, you go on iteratively refining that trial solution, right? Here also, see, Newton-Raphson search, golden section search, all these processes are like that. All these processes are like that. Here also we do the same thing. We start with a uniform distribution or a Gaussian distribution, a very easy probability distribution. Then there is a neural network which converts this initial distribution into a more complicated distribution, probability distribution, which should match the underlying spatial distribution of the object at hand with the training data based on which we will do that, right? That is the main idea. So basically here, the neural network is mapping one probability distribution into another probability distribution. That's the fundamental idea of generative models. So here is a transfer function computed by a neural network. There is an input distribution. This is just a schematic example. This input distribution must be converted into a complicated output distribution by the neural network. For generative models, for normal neural networks, for a classifier neural network, the input is a feature vector, the output is just a scalar class, scalar number indicating the class. For the generative model, for the generative neural network, the input is basically a probability distribution, and the output is another probability distribution which very closely matches the distribution of the training data. That is basically the idea. How does a neural network learns such a transform function for converting one distribution to another distribution? Let's try to give you intuitive reasoning for that. Suppose you have a neural network which has 25 inputs and 25 outputs. 25 inputs and 25 outputs. At the input, you provide it a 25-dimensional vector, which is completely random. Each entry can be 0 or 1 with 50% probability, 50-50 chance. So it's a completely random vector. 1 means completely white, 0 means completely dark. So it's a completely randomized vector of zeros and ones, and you give it to the generative network, this neural network. The neural network processes its entries and creates another vector, 25-dimensional vector, Now you unpack this 25-dimensional vector in the form of a 5x5 image, as you can see here. And you have 3-4 such 5x5 images which have a dog-like shape, tiny dog-like shape. Dog means this sort of a shape in the middle. Now the image returned by the neural network, if it does not have such a dog-like shape, then you measure how much this output image differs from the dog-like shapes that you have. Based on this difference, you define a cost function. Based on the gradients of the cost function, you go back and adjust, tune the weights of this neural network. If you go on doing this exercise again and again, so every time the neural network gives an image, gives a vector, basically you make the vector into a 5x5 image, you don't see a dog-like structure, return back and adjust the weights of the image, of the neural network, until, so when this training process converges, what will happen? Whenever you will give a random uniform vector, uniformly randomized 25-dimensional vector at the input, this network now will manipulate all these vector components in such a manner that the output vector, when unpacked in the form of an image, will show you a dog-like shape. So what do we then most dramatically say? We will say this neural network has learned to convert a uniform 25-dimensional probability distribution into a distribution which best mimics the dog-like shaped images, the probability distribution of the dog-like images, 5x5 dog-like shape based images. This is how the neural network can learn distributions. Okay, just a rough idea. I don't know how many of you got it. But the idea is we can simply do with a single network. But Goodfellow and his team went one step forward. They made the same thing happen with a competitive 2 neural network system. So in GAN, there are 2 neural networks and there is an indirect training procedure. This indirect training procedure is the main crux. And this is the schematic diagram of GAN. There are 2 neural networks. One is the generator network. This generator network could be made by a deconvolutional neural network. Deconvolutional neural network means a convolutional net in reverse flow, where the input could be a vector of random noise and the output could be an image generated from that noise vector. So the generator is a neural network. It could be a convolutional neural network in reverse flow or the decoder part of an autoencoder. If some of you have gone through autoencoder, it could be the decoder part of an autoencoder. The discriminator is a normal feed-forward neural network, which could be even a 2-class classifier. Just a 2-class classifier network. Now, these 2 neural networks, what do they do? The generator network tries to generate images initially from random noise. It doesn't know how to generate proper images. What is the goal of generating such images? Initially, it generates just like novice people. You give a pencil in the hand of a 5-year-old kid and he or she will draw some rough figures. The generation is initially like that because that 5-year-old kid has not learned anything, has not learned how to draw. So initially the generator is also such unlearned a neural network which generates ghost-like images. You have at your disposal a set of realistic images of a particular kind, like celebrity faces, as you can see here. The discriminator is a 2-class classifier whose output may be made continuous. The discriminator gives a single scalar output, which is very high if the discriminator finds that the generated image looks very realistic compared to the real faces. So if the discriminator thinks that the generated face is very realistic, then the discriminator will assign a high number to that face, that image. Otherwise, the discriminator since the discriminator has already seen these realistic images, this neural network will assign a very slow score to the generated images. So what do you think? What is happening? The generator generates images. The discriminator compares these images with the realistic images which is given to the system as training images, and tries to catch the generator that, hey, you have generated a fake image. So the generator tries to fool the discriminator. The discriminator tries to catch up the generator. Usually the discriminator initially wins, and the generator initially learns, okay, if I generate such bad, ugly images, I am having a very low score assigned to me by the discriminator. So I must improve. So there is always a competition, a tug of war between these two neural networks. And through this competition, both of the neural networks actually improve each other. So it is much like a game between fake currency producers and the police. There is a group of people who always try to, publish fake currency notes, which look very realistic, but there is also police. The police is also very clever. They try to, catch up these fake currency dealers. Some of them are jailed also, but the rest learn from the mistake of these people who are jailed. And they try to produce even more better looking, more realistic looking fake currencies. And the police sometimes also get baffled. Is that clear? Similarly, the discriminator and the generator competes with each other. And this way, we say in terms of game theory, we say they are playing a two-player zero-sum game with each other. Okay? That is very interesting. They are playing a two-player zero-sum game with each other. Let's see how it actually happens. So the generator, as I said, the generator is a system which is based on neural networks. And the generator initially accepts vector at its input. The generator initially accepts as its input. It is a simple neural network. It might be a deconvolutional neural network. That means a convolutional net in reverse flow. So the generator accepts a vector at its input. This is a low dimensional vector, maybe a 2, 3, 10, 1,000 dimensional vector. And the generator generates an image out of the vector. Different vectors should give rise to different images. Okay? This is what the generator does. And these are the images generated by generator. Maybe when the generator is well trained, it's not like the initial stages. So vectors are like code vectors. We call them codes. Codes are just a nickname for vectors of high-level numbers. These high-level numbers are provided at the input of the generator, and the generator generates images from these numbers, like a deconvolutional neural network or the encoder part of an autoencoder. Now, the generator, what is the goal of the generator? Goal of the generator is to generate realistic, as many realistic images as possible. So the goal of the generator is to generate realistic images. Okay. So the generator generates an image, and there is a realistic image already in the training set. So the generator tries to make these two images as close as possible. On the other hand, what is the goal of the classifier? The classifier, given an image, makes a one-hot vector which puts this image in its right category. That particular component, the particular class, will have a 1 entry. All the other entries of the vector should be 0. Okay. And we try to make it as close as possible to the ideal one-hot encoding. That's the difference between generator and classifier. Okay. So the question is, now, where does these codes come from? How the generator learns? We go there. Next is discriminator. What is the discriminator doing? Discriminator takes X. X is an image at the input of the discriminator and it provides R. What is this R? R is a real number. It's a score assigned by the discriminator. For a good realistic image, the discriminator will assign it a perfect 1. For a ghost-like image like this, the discriminator will assign it a very low score, 0.1. Okay. So the input is an object, which could be an image, and the output is a scalar quantity, which represents how good the object X is. That is the role of the discriminator. Sometimes we also call it evaluation function or potential function, etc. Now the question is, can we use the discriminator to guide the generator? That is the essential crux of GAN. The discriminator and the generator, their training goes in an interleaved mixed fashion. Both of them improve each other. That is what we are going to see now, how it happens. So the discriminator training goes like this. I hope all of you still hearing me, and I can hear some noise in the line. I don't know where from that is coming, but you can hear me, right? All of you?
Yes, sir, you are audible.
Okay, thank you. So the discriminator training goes like this. Given a set of positive examples, where from these positive examples come? They come from the training set. Suppose you try to make toon faces, cartoon faces, henshai faces, say for example, that's a Japanese cartoon. So given a set of positive examples, as you can see here, randomly generate a set of negative examples. Who generates this set of negative examples? Generator. We rely on the generator to generate these negative examples. Now, if there are 4 real examples, there are also 4 negative examples. And the discriminator, which is a 2-class classifier, basically, just one moment. I got disconnected as it seems.
Yes, sure.
Oh, it's fine. Yeah. So the discriminator, which generates, so the discriminator learns to distinguish between the positive and the negative examples. So the images generated by the generator and the real images. The discriminator tries to learn the difference between these 2 classes. And when it learns so, it gives very slow scores to these generated images, these negative image examples, and very high score to these positive examples. So in that sense, the discriminator can be a simple logistic regressor as well. 2 levels, real images, fake images. So the generator initially generates very bad fake images. So the learning of the discriminator becomes very easy. There are 2 classes of huge difference. So the discriminator provides a score D of X to each X that it receives. Now, what is the goal of the generator? What should be the goal of the generator? The generator's goal should be to generate such good-looking images, realistic images, so as to increase the score of the discriminator. That's why this argmax is here. Okay. So the generator generates some image X tilt. When the discriminator has already learned, one learning cycle of the discriminator is over, now the fixed discriminator is used to guide the generator. Now the discriminator has already learned to demarcate between good and bad images in one learning cycle. First learning epoch has been over. Now this learned discriminator is used to improve the generator. Now the generator generates an X tilt. The generator generates such images. The generator is compelled to generate such images for which the discriminator score might be maximized. So now the generator can have a clear feedback from the early learned generator that whether its images are good or bad. And according to the feedback, the generator can actually adjust its weights to improve its capability. So generating negative examples is done by the generator, and in that process, the generator also improves itself. So the NN generator generates images. So this is the whole thing. The generator generates images. The images are fed into the learned discriminator in the previous cycle. The discriminator assigns it a score. Initially, the generator is still unlearned, so the discriminator will assign it very low scores. So the images are like these bad images. So the discriminator assigns it 0.13. Based on this low score, now the generator knows it has committed a mistake. So based on this low score, the generator updates its weights, updates itself, and generates a better image. The better image, in this whole generator learning process, the discriminator is kept locked, fixed. So the generator gives a better image. So given this better image, the discriminator upholds its score. The discriminator increases its score to 0.9. Now the generator is fixed and the discriminator is again adjusted. Okay, so this goes on and on. So the generator learns to improve its weights by using a procedure that we call gradient ascent. So the training algorithm is initially the discriminator is trained to demarcate between generated images versus real images. Once the discriminator is trained, it is fixed. Based on the fixed discriminator, the generator improves itself until it can fool the discriminator. You can see in this example, the discriminator later assigned a 0.9 score, which means the generator has did a good job. Once the discriminator is fooled by the generator, again the generator training continues with the newly generated images. Sorry, again the discriminator training continues with the newly generated images. Once this second training cycle of the discriminator completes, the generator is adjusted based on the feedback from the trained discriminator. And this goes on. Discriminator trained, generator fixed, generator trained, discriminator fixed, then again discriminator trained, generator fixed. This is the training cycle of GAN. And it goes in this manner. Initialize generator and discriminator with random weights, which is always the case for neural network. In each training session, sample some real objects from your training set. You must have a training set full of real objects. Generate some fake objects by using your generator like this. These are the fake objects generated by the initially untrained generator. The discriminator learns to demarcate between these two classes of images, real versus fake, and updates its weights. By when this training converges, the discriminator must provide 1 score to the real images and 0 score to the fake images. Once the discriminator is updated, it is kept fixed. Now the generator generates lots of images and these images are examined by the trained discriminator. So based on the feedback from the discriminator, the generator weights are updated. Okay, until the discriminator provides almost 1 score to the newly generated images from the generator. Then we say, yes, now the generator has done a good job. Okay. Then this trained generator is again used for updating the discriminator. This is what is going on. The trained generator generates new images. The discriminator again learns to demarcate them. So this is the learning of the discriminator, D, and this is the learning of the generator, G. These two cycles proceed hand in hand. Okay. So benefit of GAN from discriminator's point of view, the discriminator can generate, the discriminator can use the generator to generate negative examples. The generator tries to make itself efficient by pushing up the scores assigned by the discriminator. From generator's point of view, it still generates the object component by component, but it has learned from the discriminator, which is gradually developing a global view by moving through different batches of images from your training set, sampled from your training set. So 3 main cycles can appear, 3 main stages can appear in the GAN training sample. We sample a mini batch of training images X and generator code Z. and we update the G and D, the generator and discriminator, by using the famous backpropagation algorithm, and by using different, actually we use a simple loss function for both of them. Different components of the loss function are used. The three, I am not going into much mathematical detail because that might be boring for many of you. Who are interested, you can read it. I will show some of it. The three situations of the training cycle go like this. First situation is false negative. The discriminator takes a real image and marks it as fake image. What does it mean? The discriminator is doing a poor job. So the error function is fed back, and based on the gradient of the error function, the discriminator weights are updated. False negative. True negative, the generator generates a fake image. The discriminator says, yes, it is fake, by assigning a very small score to the image. What does it mean? Who now requires adjustment? Who now requires improvement? Obviously, the generator. So based on the error function, the generator is updated, as you can see here. The third situation is the generator generates a fake image, and the discriminator says, yes, it is, sorry, the discriminator says, yes, it is real. The discriminator provides a high score to the fake image. Now who requires updating? Who requires improvement? The discriminator. That is the false positive scenario. So based on these three scenarios, the GAN training goes on. And at the end of the training, if we are lucky enough and the GAN training has gone through a very good optimization scenario, then at the end of the day, the situation that we arrive at is called Nash equilibrium, after the famous game theorist and Nobel Prize winner John Nash. So Nash equilibrium is a scenario after which these two networks can no longer improve each other. That's when we say, okay, the training has finally converged, but GAN training may not proceed to Nash equilibrium. There are lots of problems in GAN training also, but that is the ideal scenario. Okay, the Nash equilibrium has been achieved. So the GAN training cycle modes, as I was telling, initially the generated distribution looks like this, and the true distribution is supposed something like this. So the generated distribution is, now if I look at it from a probability point of view, the generator is actually trying to mimic the underlying distribution of the training images. So the initial distribution is very bad. The discriminator easily captures generated images from such poor distribution that they do not belong to the true distribution. So the generator loss is calculated. Let LD be the generator loss, which is a function of the generator weights. So the gradient of that loss is taken and the generated neural network weights are adjusted. Generated distribution is not good at all. After the generator improves, it generates some distribution which is still not close enough to the true distribution. So the loss of the generator is once again updated. Based on the loss of the generator, the weights are once again updated. The generator has improved, but the data is still not good enough to fool the discriminator. Now, after the generator has improved significantly, now the discriminator assigns a high score to the generator scenario. So now, based on the gradient with respect to the discriminator weights, the discriminator needs improvement. So this is how the generated distribution has once again been updated, and now the discriminator has been fooled. This is the picture where it is happening. When the generated distribution is pretty close to the true distribution, the discriminator might have been fooled. Now the discriminator weights are updated based on the gradient of the loss function with respect to the discriminator weights. And this is done so that the generated distribution next time becomes close enough, closer, fine-tuned to the generated distribution. That's why this is done. This process continues theoretically until the generated distribution is indistinguishable from the true distribution. When that theoretically happens, we say, okay, The two networks has entered into the Nash equilibrium. That's the dream of every GAN scientist, so that their training may converge. This is just an illustration. So the real data, the real distribution is circular. The blue data is the circular distribution. And the orange dots are the generated data. Just two dimensions. As you can see, GAN can very quickly arrange the generated distribution to mimic the real distribution. VAE is another deep generative model that is called variational autoencoder model. For VAE, it takes quite a lot of time to mimic this easier distribution. However, GAN is not meant for so simple things. GAN is meant for something very different. GAN is meant to mimic the distribution of multivariate high-resolution images. And here are some results. If you look at these results, these horses, these sofa sets, these are various classes of images. Sofa sets, horses, buses, churches, cycles, none of them are real. All these churches are never found on Earth. These images were all generated by GAN. After they were trained with similar images, these images were generated, fake, artificial. Okay. How GAN images evolved with time. In 2014, at the time when we didn't have enough GPU, enough iterations, we cannot go with the backpropagation. We had such hazy, artificial looking images. But now we have 2017-18, if you look at this big GAN project images, progressive GAN images, they are so realistic. You can see the pimples on the skin, you can see the wrinkles, you can see the gray hairs. 2017, this particular image is taken from the famous celeb dataset. So GAN was trained with the Hollywood celebrities images, Tom Hanks, Tom Cruise, Angelina Jolie, Brad Pitt. And after some rounds of such training, GAN generated its own face of celebrities, none of whom were born on Earth. Got it? So this is how the GAN images, fake images, these people never exist on Earth. So how these images improved with time. And not only face, if you look at the recent Big GAN project by DeepMind, they can generate images from almost all classes of the image-led data set and much better quality images, like this pasta, this bubble, this coffee mug, this dog, space shuttle. These are all generated by GAN. Okay? They are not real. Now, the research on and with GAN has reached almost its peak. A new GAN is coming almost every week. And if you look at this particular GitHub page, which provides us with the GAN Zoo, you can see how the new GAN algorithms are coming for various purposes of improvement. Okay. So lots of such things are happening. Let us take a look. I don't have that in this slide, so I have to just change the slide a little bit. Let me just stop the sharing for a little bit and just share a very different screen. Just hold on. Yeah, so hope you can see this particular slide just for the sake of completion.
Yes, it is visible.
So the GAN objective function looks like this. What is E? Don't be afraid by looking at this E. This E means average, expectation. So for different training samples, you have different training samples. Suppose X is a real training sample. This X is a real training image. Dx is basically the score returned by the discriminator for this real training image. Log of dx is the logarithm of that score. And E means X coming from the original data set. This X tilde P data means X is coming from the original training data. E means you are averaging all these logs, expectation value, which is here simple averaging. Okay, and so expectation value, which is here simple average, right? So E of log of GX is basically average of the scores assigned by the discriminator to real images. This part has to be maximized. The discriminator weights should be such that this part is maximized, because the discriminators should assign high scores to X. So if dx is close to 1, log of dx is close to 0. And if dx is close to 0, dx should always be between 0 and 1, like dx is 0.1, 0.3. Log of dx is negative. So maximum value means towards 0 for this part. What is this next part? This next part is the average of the scores assigned to the generated images. Z is a random noise. Z is the code vector. G of Z is the image generated by the generator from the code vector. D of G of Z is basically the evaluation of discriminator on that generated image. So the discriminator takes the image generated by the generator and assigns a score to it. That score is D of G of Z. Don't be afraid by looking at this. So 1 minus D of G of Z is basically the reverse. If the discriminator catches up the generator, it will assign very small score to the generated image. So D of G of Z will be close to 0. 1 minus D of G of Z will be close to 1. And the logarithm will be close to 1. So this function is a function of two things. D, which is the set of weights in the discriminator neural network, and G, which is the set of weights in the generator neural network. This function should be minimized with respect to the generator. Generator, when we look at it from the perspective of the generator, generator has nothing to do with this first part. Generator will attack the second part. Generator will try to generate such images for which D of G of Z will be very close to 1. As a result of this, this logarithm of 1 minus D of G of Z will be very close to negative number. Negative, that means smaller. So the generator tries to minimize this part, the second part. The discriminator tries to maximize the whole thing. And this is called the min-max value function in game theory terms, but this also gives us the objective function of GAN. So the GAN's objective function, the discriminator's cost function is basically this thing, this average minus log dx, because minus is done provided to so that it could be minimized. The minus of log, because actually these terms are negative for for dx or d of gz values, which are not exactly 1 but between 0 and 1. That's why a negative sign is sometimes added to counterbalance the negative. This is nothing but the cross entropy loss, those who know that. So discriminator cross function is this one, and the generator cost function is basically constant plus this one. This constant has nothing to do. The generator tries to maximize this log of 1 minus d of gz part. And these two functions combinedly is called the min-max value function, which serves as the GAN's objective. Now I will again switch to the other slide. So I will again switch to the other slide. So up to this, you have seen what GAN does, how GAN, there are two neural networks, how they improve each other. GANs are well known for creating artificial images. which look very realistic. This has good use and bad use both, like all other sciences. Now the gentleman, I will just illustrate an example of it and conclude. The gentleman's data means the ideal data. Machine learning, most of the machine learning algorithms usually work on such assumptions of ideality. One such assumption is all classes are equally represented, which is very frequently not true. When we are trying to diagnose a disease, like the example I put forth at the beginning, malignant versus benign. So when the oncologist is examining 100 randomly sampled images, breast mammograms, maybe 4 or 5 of these mammograms will turn out to be malignant. The rest will be benign. So in the training set, one class, the malignant class, which is the most important class, will have only 4 members. The benign class will have 96 members. So if a machine learning algorithm is trained on this data, which we will call an imbalanced data. Imbalanced because one class is very poorly represented. So if we do it on this imbalanced data, what will happen? If the learning algorithm gets biased towards the majority class, where there are 96 representative examples, it can learn only that class. When a new, so all new, the training examples that come, it will demarcate, it will just stamp it as a benign. On the training set, what is its accuracy? If it assumes all the 4 malignant cases are benign, if it wrongly stamps them, what is its accuracy? Still 96%. Because out of 100, it is stamping 96 benign examples correctly. Only 4 malignant examples wrongly. But what is the implication? Dangerous. It has missed the target minority class. It has said a cancer patient, no, you are normal. And the cancer patient becomes very happy for the time being, doesn't start chemotherapy. And after 1 month, his condition is very bad. You understand? So sometimes in the computer-assisted disease diagnosis, so this is very, very crucial. It's like you have practiced sums from 2 chapters, limit and continuity and permutation combination. From limits and continuity, you have practiced 100 sums. From permutation combination, you have practiced only 5 sums. So in the final exam, you will be very confident on a limit sum, but you will be very disconfident on a sum from permutation combination, unseen sum, because your training on that particular chapter is weak. Similarly, when the training data has dissimilar examples from 2 classes or 3 classes, the training on the minority classes becomes very weak, disconfident. This is the problem of imbalanced classification. Okay? So machine learning relies on such ideality assumptions. Life is hardly so easy. So what happens is different data irregularities come into play. One such major irregularity is the class imbalance. Okay? These data irregularities pose very tough challenge towards machine learning. And class imbalance is nearly everywhere. They confuse the learners like this. And they cannot actually figure out how to not miss the minority class. Okay? So what happens is, so this is the class imbalance problem. There are very few examples from one class and lots of examples from the other class. Natural disaster prediction, fraud detection. We worked in a National Payment Corporation's project. National Payment Corporation is a consortium of banks from India. And whenever an online transaction happening, a 61-dimensional feature vector characterizes that transaction. And a copy of that transaction is actually stored in the server of NPC, National Payment Corporation of India, NPCI. Our job was to predict fraudulent transactions from genuine transactions. Do you know how many online transactions happen in one day from India? Post-log, this is pre-lockdown. That time there was no corona. So at that time in one day, now it has increased, I think. At that time, in one day, there were almost 1 crore transactions, more than 1 crore, I think. 1 crore, 10 power 7 transactions. Out of the 1 crore transactions, how many were fraudulent? Hardly 5,000 to 6,000. So do you see there are two classes, fraudulent versus genuine. The genuine class is so huge, fraudulent class is so meager, only 5,000 samples. So that's a huge class imbalance classification problem. One way to mitigate the imbalance classification problem is to oversample. Oversample means let us generate more artificial points in the minority class, which bear all the traits of the minority class. That will help us to put the decision boundary properly. So what SMOT does is, it measures the distance between different minority class examples. It actually joins this new query point with the nearest minority class points by straight lines in the feature space, if it is a very easy feature space. And then it creates new points as a convex combination of these minority neighbors. These new points populate the minority class. This is called artificial data balancing. And the minority class appears to be nearly as populated as the majority class. And the classification decision boundary can go well between them instead of getting biased towards the majority class. However, SMOT has lots of good things and bad things as well, especially when it comes to image classification. The end-to-end system, oversampling for the end-to-end system becomes very difficult by using a single SMOT. One first work in this area of deep oversampling was reported in, I think, CVP 2017 by Andrew and Huang, who incorporated SMOT between the convolutional layers in a normal convolutional neural network. We proposed the GAMO. GAMO stands for generative adversarial minority oversampling, to populate the minority class by generating artificial synthetic examples. And GAMO was published in ICCV 2019, which is one of the largest computer vision conferences. I will not go into the details of GAMO because I don't have enough time. The paper and the codes are available from the arXiv link here for everyone. All the codes are available publicly. I will just give you the idea and conclude. Idea will be given in terms of pictures. So I'm not going into all these things. So this is the idea. Suppose you have two classes. One is this blue class, which is very populated, may have a non-convex distribution, which is one of the difficult most situations to classify. Non-convex distribution of blue points. The other is the red points, which denote the minority class examples. And between them, if you do nothing, just put a regular convolutional neural network classifiers, it learns the classification decision boundary like this. And the decision regions are this bluish region and this yellowish region. It is bad. Why it is bad? Because lots of minority points are misclassified. These are all, false negative. False negative situation is not good. So these are all like patients who have cancer and the machine says you are okay, you are genuine, benign. So that's the situation with unaided classifier. Okay. Now, if I add a convex generator, and the convex generator is something which generates images in a interpolated convex hull of the minority class. So if I generate convex generator, it creates lots of artificial green points, which are the oversampled artificial points to populate the minority class. So if we do this, what happens? These green points are generated and the classification decision boundary changes like this, but lots of majority class points who are here, these blue points have also been misclassified. So the blue points are also misclassified. This is another pathetic situation, which is called false positive. False positive. You don't have cancer, and the machine says, yes, you have cancer, and you started chemotherapy. That chemotherapy damages tissues in your body to a vast extent. For COVID-19, it's fine. I don't have corona, but the diagnostic center says, yes, you have corona, which is mostly happening everywhere. So I start taking Kara, I start taking zinc, vitamin C, minerals, etc., which is not as bad as this situation. So, you know, I mean, false positive and false negative has different implications in different scenarios. But it's still not good, right? So what GAMO does is, GAMO plays a three-player game. It adds a convex generator, a classifier, which says how difficult the region to classify is. Usually the difficult region is this region where there is an overlap between the two classes, this portion. So GAMO also adds the discriminator. So the structure of GAMO is a three-player game. Normal GAN is a two neural network system. GAMO is a three neural network system where the additional discriminator can actually spread these ring points uniformly inside the minority class, as a result of which a nice classification decision boundary can be learned. And the classifier doesn't get biased towards either the minority class or towards the majority class. That's the basic idea of GAMO. Okay? And this is how the probability distribution improves, but I don't want to explain this picture. This is too typical for probabilists. This is the GAMO architecture. We have some conditional transient mapping units, some image generated, convex generator is basically this full thing. And then there are conditional discriminator, and there is a classifier network. And these are the three different cost functions for the three different parts of the system. I'm not going to explain it fully because it requires a lot of mathematics. If you are interested, please see the paper or drop me an email. So compared to many other algorithms, especially this deep oversampling from CVP of 2017, this CDC GAN plus convolutional net, augment plus convolutional net, simple smooth plus convolutional net on state-of-the-art datasets like fashion and NIST. These are all very complicated image datasets. We had a very high score and good score basically. And we could also avoid lots of mode collapse. Mode collapse is a big problem in vanilla GANs. Actually, mode collapse means if your training data has internal classes, like MNIST has 10 different handwritten digits, the generator generates only one class very nicely and fools the discriminator. After that, in the subsequent training cycles, it will continue to generate the same class again and again. If the generator can fool the discriminator with, sorry, I just spoke a little bit in Bengali, but this is for my Bengali friends here. So the discriminator, if it can fool the generator, if it can fool the discriminator with very nicely constructed image from one particular class, it will go on generating that image again and again. So this is the situation where only the one is being generated. 2, 3, 4 other images are not being generated. So mode collapse and training stability is a big problem of GAN. GAMO can achieve both of these. Actually, GAMO 2Pix is basically converting the oversampled images into oversampled synthetic points into images. And as you can see, here is the mode collapse. If you look at these faces, these are the faces of the same person, generated again and again. Same shoe. But if you look at the GAMO generation, you will see that the images are different. Actually, this was run for less number of epochs on our limited computing facility. That's why the images are somewhat hazy. But you can see from even from different classes, you have many distinctions. It is not that the same instance is again and again generated. So this is mode collapse. Do you see mode collapse? Yes. And in case of GAMO, we see different images. Although this is the face class. So even in the face class, you have different faces. Similarly, in other classes, you have different objects. This variability is very important to give more experience to your classifier, right? So that's it. Future, coming to the future, one big future is deep neuroevolution. Evolutionary computing is coming back in a very big scale because deep neural networks have lots of hyperparameters to tune. And instead of relying on the random trial and error methods, why not evolve these hyperparameters like human brain evolved for millions of years from the time of Neanderthal man to the present age. So deep neuroevolution tries to find out the hyperparameters of a deep neural network by using the Darwinian principle of evolution and natural genetics. Here is a nice survey which captures the whole field, summarizes the developments. Facebook AI, Uber AI, also Google nowadays, the DeepMind. These giant industries are, investing a lot of money behind this evolutionary research in deep learning. This is a recent paper in IEEE Transactions on MAKAUT, which is actually evolving the generator network of GAN by using genetic algorithm principles. Okay, so that's the eGAN, evolutionary GAN. And it gives quite nice results. Style transfer is another very interesting problem. This is a very famous GAN paper called Cycle GAN paper from 2017 ICCD, the same conference where GAMO was published. So this paper, this is done by the California Berkeley people. This paper actually says it uses a GAN architecture which can transfer the style of one image into another image while preserving the content. So if you train Cycle GAN with the hand-painted images by famous artists like Monet, Van Gogh, Cézanne, Ukiyo, etc. If you upload a photograph, clicked photograph, into your system, the Cycle GAN will import the drawing style of different artists into your photograph, and it will show you how your photo looks like when it is drawn by one of these artists. That is the idea of style transfer. Similarly, it can show you how horses look like when they have marks like zebra, how a landscape looks in summer for winter or winter for summer, this sort of things. Future applications include generating more high-resolution images, photorealistic images with GANs, as you can see. Developing a neural photo editor, behavioral photo editor. You just put the cursor somewhere here or here or here, and it shows you how your hairstyle looks like. It automatically adapts the hairstyle with your face. Pix2Pix is a cool image-to-image translation system which is following somewhat similar architecture as Cycle GAN. So given a map, it will show you how the original landscape looks like. Given sketch, it can generate the original object and so on. That's a Pix2Pix. It's a quoted cross-domain GANs paper. And latest one is how to transfer. So the style transfer also goes into speech also. I can now, the speech style transfer is a hot topic. I didn't have a slide for that, but that essentially means that the voice texture of somebody else is imported in my voice. Just like I want to adapt the voice texture of Mr. Bachchan, Amitabh Bachchan. So Amitabh Bachchan's voice, Cycle GAN is trained with Amitabh Bachchan's voice, and that texture is imported into my voice. So this GAN lecture will be mine, but instead of my voice, the baritone will be from Mr. Bachchan. Such things are coming up very quickly. You'll see some apps, like Face app, you have seen it. Last one is this one. So you can bring older photos to, this is just from, I think, CVPR 2019. So you can import your expression into a famous old painting, like how Mona Lisa looked like if I don't know whether you can see this GIF properly or not, but it shows how you can impose an input expression on Mona Lisa and how she looks like with your expression. Okay, so many cool applications are there.
Yes, it is visible. Yeah.
Visible.
It is visible.
So see, this way, when you are generating artificial images, you are imposing one's expression into another's expression. These can be used for both good and bad purposes. Right? For example, deep fake is basically, they were actually warning us, adversarial things can be done. Deep fake were generated fake news clips of hate speeches, famous people who actually didn't spoke those things out. So this way you can generate fake message, fake news, fake images and trigger a riot. Or you can generate artificial samples to balance your imbalanced class, to give more accurate predictions on fraud detection, etc. Science is always either a blessing or a curse. You have to decide that. That's why nowadays the AI and ethics courses are going hand in hand everywhere in foreign universities. Geoffrey Everest Hinton is he's the godfather of deep learning, I should say, one of the major proponents of backpropagation algorithm, deep neural networks. After so much research on all these things, he still believes we are light years away from understanding how human brain actually functions. We are light years away. And he has recently remarked that the future depends on some graduate student who is deeply suspicious of everything I have said. So nobody knows. Go on questioning and doubting things. From your doubts, some new areas may emerge in the future. These are some resources that I must acknowledge. Many slides are taken from these resources. This is the only nice book written by Goodfellow, Bengio, and Cornville on deep learning. Absolutely freely available. In fact, in machine learning and computer vision, all the top conference papers, be it ICCV, CVPR, ICML, NeoWIPS, all the papers are freely available. You don't have to pay any money to Springer, IEEE, Elsevier, nobody. Thanks to Geoffrey Hinton and his academic students who believed that the academic material, the scientific material must be accessible to everyone. Even, it doesn't matter whether you subscribe to some publication house or not. And indeed, all these resources are freely available. This is a nice tutorial by Yoon Hee Lee from NTU. I have used some slides from this tutorial also, you'll see the acknowledgement. There is a nice Brandon Rohr tutorial on LinkedIn, CycleGAN tutorial by Roger Grosset, etc. So you can use these resources if you wish. So with this, I would like to conclude and thank you for the questions. If you have any questions, I can
Thank you
take.
very much, sir, for your illustrative and illuminating talk. And we are almost approaching to 2. So I think within next time, we can have questions that are posted in the QA area. There are 11 questions posted. So Sriporna
Okay.
ma'am, please can you please go with the question answer session?
Yeah, okay, sir, with your due permission, I'm reading out
Yes.
the question. Okay, first question, actually the first question has been by Mr. Omeo Sarkar, how human sees and how machine sees. Same way
Well,
he has, yeah.
yeah, okay, I can now read this question, yeah.
Yeah.
See, this is this is a nice question though. Human sees by eyes, and the eye is a very high resolution, very high. Like if you try to measure it in megapixel, it comes to absolutely crazy numbers. So eye, you know how it focuses images on retina, and from there, nobody knows exactly how the visual perception, especially the depth develops, that you are far, I am near, etc. The third axis develops. So human brain computes the 3D perception of images from the 2D images cast on the retina. And this, the computer vision people try to imitate that in various ways, taking baby steps towards the actual mechanism. Machine always sees by using cameras. So given a mobile robot, it has cameras mounted on its top. These cameras have some kind of refresh rate. They take images from real world and tries to, you know, it can have 2 cameras. It can take 2, 3, 4 images of the same area Then by fusing these images, it tries to develop a 3D perception. So how human learns, I explained. We learn with the help of a teacher. Sometimes we learn by interacting with our environment. In that case, we call it a reinforcement learning. So there is a baby, and the baby is in a room. There is a candle flame, and there is a ball. The baby touches the ball, plays with it, gets fun. Goes to the candle flame, tries to touch it, gets burned. So this way, he actually interacts with his environment, and without any teacher, he can also learn that the candle flame is dangerous. I must keep away from it. This is the idea of reinforcement learning. So the machine learns by imitating the human beings. Supervised learning, just like human being learn from mother, father, other teachers, similarly machine learns by taking inputs from a human expert. Reinforcement learning interacts with the environment. Unsupervised learning, human beings also learn many things unsupervisedly. Human beings, unlike the machines, like GAN, I was talking about GAN. GAN has lots of, requires lots of training images, lots of training images. Human beings sometimes may not require so many training images. If you see the image of a giraffe printed in your book, and once you know it is a giraffe, single image suffices. Do you need to see hundreds of giraffes or 500 giraffe images to really recognize a giraffe when you go to a zoo? No. This is something that machines are yet to follow. Machines require lots of, almost similar training images to develop a perception. But human beings can do so by looking at 1, 2 images. It's a remarkable difference. Machine learning nowadays has a facet called few-shot learning, zero-shot learning, where we try to imitate this. Another question is, okay, let me see the questions. I can now see them here. How max pooling works in deep learning, how it reduces the dimension. Yes. Max pooling actually divides the feature map into 4 or maybe an even number of slices, and from each slice. So for example, if you have a 16 cross 16 matrix, you have 256 dimensions. So now you take 4, 4, 4, 4. Oh, sorry. Say for example, you have 8 and 8, 8 cross 8 matrix. So you have 64 numbers. Now you divide into 4, 4 blocks. And out of the 4, 4 blocks, from every block, you keep the maximum number and discard the rest. What happens? From 64, you have only 4 numbers. Okay, that's a reduction. That's a downsampling. Okay, so max pooling is an operation by which we divide a whole matrix into sub-blocks, and from each sub-block, we either keep the average value, or we keep the maximum value, or we keep the nearest neighbor value. There are various types of pooling operations. So that's how it reduces the number of dimension, number of features. Okay. Can we use GAN for detecting handwritten digit images? Of course. GAN can be very nicely used for MNIST image classification and recognition. MNIST is basically the collection of handwritten digital image. This is a very trivial problem for GAN, almost nothing. Which neural network we can use for discriminator and generator? As I said, discriminator can be a 2-class classifier. It can be a logistic regressor. Generator can be either deconvolutional neural network, convolutional net in a reverse form, or it can also be the decoder part of an autoencoder. But if you are dealing with, my talk was completely on images. If you are dealing with, text or biological sequences, in those cases, you have to use recurrent neural networks or RNNs to create the discriminator and the generator. Okay. Another question from Paramita Ray is, can we use this GAN network for time series prediction? Of course. Time series prediction has an additional challenge. Sometimes in time series prediction, especially for the, if it is a short-term prediction, and if the time series is having a lot of flickers, so the underlying distribution function changes. So the time series GAN tries to, or GAN can be adopted. This is the current state-of-the-art research where GAN can be adopted not only to imitate a probability distribution, but also to track the changes in the distribution that may occur with time. So GAN can be used to track the changes inside the distribution of a dynamic probability distribution. That is the main facet in time series prediction. There are lots of papers on GAN plus time series predictions. Generator only follow uniform distribution? No. Generator, initially people used to use the uniform distribution as an input to the generator, and the generator converts it to more complicated distribution. Now much better scenarios are there. So sometimes people use mixture of Gaussians. There is a beta GAN also. Beta distribution is kind of a mother distribution from which many other distributions can be made as special cases. So GAN generator can use beta distribution also as the input to get much better solutions. As the generator and the discriminator have different training processes. So the GAN training as a whole is basically the training of the generator and the discriminator, and these two trainings go in an interleaved fashion. First, generator is unlearned. Discriminator learns, discriminator weights are updated. Then based on the updated discriminator, generator weights are updated. Based on the feedback from the updated discriminator, generator weights are updated. Then based on the images generated from the updated generator, discriminator weights are updated. This way both go hand in hand, and that is the whole training. Generator to detect particular portion, this is a very good question from Subroto Jana. Yes, that's what we call conditional generation. So you can try to generate even you can take patches from your image. For example, I want to generate different types of noses from a face, different types of eyes. So you can take patch of the face image and you can train your generator to generate very different types of faces only. The rest of the face, sorry, very different types of eyes only. The rest of the face can remain unchanged. So you can have conditional GAN, is a specific GAN for where the generator training is actually constrained or conditioned on specific parts of an image or specific types of the image. So that's a very well established area. Which method can we use for hyperparameter tuning for GAN? This is a good question. As I just said, there is no well-established method for hyperparameter tuning. Hyperparameter tuning is done by trial and error, series of tuning experiments. Only thing that we can have now is evolution. Darwinian evolution and natural genetics principles can be used. You can have multiple structures, you can do crossover, you can do random changes in some structure, which we call mutation, but these are computationally very expensive. So if you ask me what is the hyperparameter tuning mechanism, no straightforward mechanism. You can follow, but lots of guidelines are there because so many people are working for over last 6 years. So from their studies, lots of guidelines, lots of experiences have emerged that if you keep this sort of activation function, if you keep these many hidden layers, then for such and such images, probably you will get a good result, etc., etc. Probably. There is no hard and fast rule. There is no theory, right? How to identify and diagnose GAN failure models? One is the training doesn't converge. So you will see the weights are not actually properly updating. Second, that is the stability issue in the training. Second is mode collapse. You will see that the generator is generating same image again and again and again. And the discriminator is saying, yes, it's a good image. So if that happens, that is the terrible problem of mode collapse. Mode means internal variations inside the training set, and the GAN fails to capture those internal variations. It generates the same image again and again. So that is a clear indication that the GAN training is a failure. Probably you need to update your optimizer. Which are the research areas where GAN be applied? Now it is almost, computer vision, 3D reconstruction, IoT, distributed intrusion detection system, anomaly detection system, then medical image diagnosis, medical imaging, obviously obeying certain rules, imbalance classification, communication systems. There are lots of issues in adversarial attack design, self-driving cars, automatic detection of traffic posts against adversarial attacks. What type of attacks can come? Visual cryptology, everywhere you can see lots of applications of that. So I think I have given some answers to almost all the questions. Thank you once again.
So there are two other questions. One is, can I read out if you have
Yes.
time? Okay,
Yes.
one question is by Probal Roy. How can GAN be applied to real-time application like analysis and processing of video stream feed?
See, real-time application is possible with a trained GAN. So you need to train it offline because training requires a lot of time. GAN training with modern days GPU machines, obviously you can use Google Colab, but they have certain limitations. So to do real working with GAN type of systems, you need to install GPU or GPU clusters. If you have such things, it still takes 1 hour or more for a big data set for GAN to be trained. So that training cannot be done online. Only thing is, if it is trained on specific types of images, sometimes by using transfer learning. Transfer learning means that perception can be used for other things. A human child who has seen trucks, he has seen only trucks, but he can still identify four-wheelers as vehicles similar to trucks by transferring his actual visual knowledge from trucks to ambassador cars or other types of cars. Same thing can be done by GAN also. In real time, that transfer learning is possible. Also, it is possible to use this trained network very quickly, because when it is trained and it generates a new image, that can be done very quickly. Only the training requires time. Okay, so a trained network can be used for real time. What is the next question?
Another is in the chat box, that is Piyush Kanti Dotto has asked, what are the other application areas of GAN besides imaging and computer vision?
I already told.
One is you have told speech.
Yeah.
In the speech also.
Yeah. So speech industry is heavily reliant on relying on GAN these days. Artificial speech synthesis, speech synthesis based on different emotions, which is used for this human computer interfacing, where you may want to provide some consultations, machine based consultations to mental patients or depressed people. So for that, you need to generate different speech waveforms with different emotions. So as just I mentioned, conditional GAN. So you are generating a speech waveform. Suppose some artificial voice is reading something. This has been there as a PDF with the Adobe PDF for a long time. PDFs can be automatically read out, isn't that? But now, suppose I am telling a funny story to my daughter. She's a kid. So I'm telling a funny story. I want the computer to tell a funny story. The voice should be jovial and fun-filled. How can I generate such emotionally conditioned speech? Big thing. Nowadays, automatic dubbing is coming. After a few years, I don't know what will happen to the movie industry. Movie industry, the special effect industry, special effects in movies, visual effects, speech effects, artificial dubbing, highly relying on GAN-based technologies. So similarly, speech, music, communication sciences, anomaly detection, visual cryptology, attack detection. Self-driving car is a major stakeholder. There is a website which contains data from Tesla 4.0, which is now running in US. The self-driving car Tesla 4.0. There is a website called Carla. It's coming from car learning. So Carla contains all these. And Carla, in case of Carla, the artificial environment in which the car will be driven is being synthesized by GAN. Okay, so this environment is for artificial virtual training of a driver who can drive his car through that environment. Same thing is happening in space technology also. Nobody has gone to Mars, but I need a terrain similar to the Mars terrain. Who will synthesize that three-dimensional image? You can use GAN for doing that. And that three-dimensional image will be used to train robotic navigators in an artificial environment where human knowledge has not gone so far. So similar applications are everywhere. So thank you very much.
Thank you, sir.
Yeah.
Thank you for enlightening speech. Every day we talked about deep learning networks, and you have taught us deep learning network from the very sketch. And not only the classification applications, by we have learned that not only classification, we can generate data as well. If there is a less amount of data is there in the, it's a another type of uncommon sort of application that we have learned about deep learning. Today we have our Professor Devashish De with us. Sir, do you want to say anything to our honorable speaker?
Yeah, nice to see.
Yeah, nice to see you, Professor.
And really happy to see you again
Me too.
in this forum. You're always kind to us, give your valuable time. And I can remember 2016, we are organizing ICAC 2016.
Yeah, that's right.
Science City, sorry, the City Center 1,
That's
the
right.
CII. So that event was grand successful. Similarly, today also you have given a lot of insights related to the deep learning. Hope that everyone will enjoy, already enjoyed, and they will get the opportunity to work with you also if you permit them.
Sure, sure.
Yeah.
Thank you.
And incidentally, you are also, the close to my house. The family is also very close to my area. Hopefully, you will meet again.
Yeah, of course, of course.
Yeah.
Thank you.
Yeah. Thank you very much for giving your valuable time, and thanks you once again. Thank you.
Sure.
Thank you, Professor De, and thank you, Dr. Shagotam Das, for your valuable speech and significant time you spent with us. Thank you so much. Now, one announcement. We would continue the valedictory session now. There will be no break. So please stay with us. Professor De, please remain connected as Vice Chancellor Sir and all others are just joining. I'm just informing because
Okay.
all the participants, please remain connected.
हाँ ठीक है
Thank you, Dr. Partha Pratim Lahiri, our registrar sir, for joining us. So we will be starting the valedictory session very soon. So please stay connected with us. স্যার রেজিস্ট্রার স্যার আর প্রফেসর দেবাশিস দে জয়েন করেছেন আর আমি বাকিদের ফোনে জানিয়েছি আর স্যার পার্টিসিপেন্টসদেরও সবাইকে কানেক্টেড থাকতে বলেছি মানে আমরা সবাই আছি স্যার Good afternoon to you all. Thanks all the participants for being with us for last 5 days and this is today is the 5th and final day and our dignitaries are joining and once our honorable vice chancellor sir Professor Dr. Shoykot Moitro joins us we will be readily starting the valedictory session. Meanwhile we have Dr. Partha Pratim Lahiri with us, our registrar of our university, Professor Debashish De, Professor Computer Science and Engineering Department and Director School of Computational Science is with us, and all the organizing committee members who are faculty members of Department of Computer Science and Engineering have also joined us. We welcome you all, and myself and Dr. Sriporna Shaha. And we are aware that there are so many webinars are being held back to back, parallel, sequential. So we are going through basically tight schedule. So that's why we are continuing with this valedictory without any break. And after this valedictory session is over, then the quiz and feedback links will be shared with all. And please submit quiz and don't forget to submit the feedback. Only then the process will be complete, and the webinar team will email you your participation certificates. So we are just waiting to have to welcome our Honorable Vice Chancellor sir with us. We have Honorable Vice Chancellor Sir, Professor Dr. Shoykot Moitro Sir amongst us. A warm welcome to you, sir, on behalf of the organizing committee.
Thank you. Continue.
Sir, can you hear me? Okay,
Yes,
so yes, sir. So good afternoon and warm welcome to all distinguished guests in the valedictory session of the FDP on intelligent computing. This 5-day long FDP from 11th.
I
Yes.
5-7 মিনিট পরে আসছি।
11th September to today, that is 15th September, is being organized by the Department of Computer Science and Engineering in association with Islamic University of Science and Technology, Jammu and Kashmir, India, and funded by TechIP3. This program theme is very much relevant in current context, and as well as this is in emerging research domain. Eminent speakers have enlightened the participants with different research wings, starting from robot automation to ethics of AI to application of AI and ML in hardware automation, applications of deep generative adversarial networks to case studies on hybrid intelligence, etc. for further exploration. Without wasting time, as our Honorable Vice Chancellor sir has to join another webinar, we welcome our Honorable Vice Chancellor sir to say his valuable words. Sir?
Okay, thank you. So it's great that you have just completed these faculty development programs, and I believe that through these programs, all the participants they are formidably benefited. And now the thing is, whatever you have learned out of this faculty development program, this is not a sacrosanct, and there is many things to learn further. And this is just you can say as initiation or a curtain raiser. So whatever you have learned, make a document of it, and try to see what further you can learn to augment this knowledge, to supplement this knowledge further. And for that purpose, I would like to advise you. I always tell to all the participants, kindly explore internet, all these online courses, open courseware, all these things. There you will find a large number of resources available, and from there, as you have already this gathered sufficient preliminary, fundamental or basic information, now to take it further will not be a difficult proposition, and you can learn easily from different open courseware and online MOOCs and all from other platforms. I can tell you the thousands and thousands courses are regularly being uploaded at online platform from different top universities. Kindly take advantage of all these things, and most of these from open courseware it is almost free, and for other platforms it is very much affordable. And here in India also we have these numbers of online repositories. So kindly look into it, and in near future we will organize maybe this advanced version of this faculty development program further. Our faculty members, they are very competent and agile and energetic. Dr. Suparna Saha, Dr. Suparna Bishwas, I can say Rupali Pato, and all other this force, this new force. They will my expectation and my conviction is that they will take the department to this computer science department to a new height in near future. And I can assure that more such types of training programs will be organized by them, and all the participants, they will get a chance further to upgrade and to validate and to brush up their knowledges. And with this, I wish you all the best, and kindly get yourselves involved in nurturing and culturing whatever you have learned, and and definitely that will give you, this right sort of dividend for your future career path. Thank you all.
Thank you very much, sir, for your encouraging and valuable words. With your kind direction and encouragement, we are progressing, and hope in future we will be able to do such programs and any other positive activities. So now I welcome Dr. Parthapratim Lahiri, the registrar of our university, to say few words.
Okay, so kindly excuse me, I have to join another program organized by this media science department.
Yes,
So you continue these programs in distribution of these certificates. I think digital certificates will be given.
Yes, it will be emailed to all the participants.
Thank you.
They will submit a quiz covering
will they
all
get
the
any
topics.
compendium of lectures like this, a digital compendium of all these lectures?
Yes, sir, I will.
Okay. Kindly see all these things. And announce that whenever you will be able to organize the next version of this development programs. I want to make it, this series, this version 1, version 2, version 3
Yes,
in
sir.
this way.
Yes.
So people will get the chance to, this upgrade themselves continuously.
Yes, sustainable learning, sir.
Yes, sustainable learning. This is the right phrase. So kindly do that and announce that whenever you will be able further to organize these types of program again. Okay, thank you.
Thank you, sir, for your time. Thank you.
Okay.
Thank you, sir.
Thank you.
Now we will hear some valuable words with our registrar, Dr. Parthapratim Lahiri.
Thank you very much. Thank you for inviting me.
Yes, sir.
I have nothing new to say.
Yes.
Yes.
Just I want to announce that the IQAC director, Dr. Somdatta Chakraborty madam, has also joined us. So welcome, ma'am. Sir, please continue.
Thank you very much. Thank you for inviting me. I have nothing additional to say because at the time of beginning I was there. So I hope that the FDP program you organized for 5 long days has been a successful one, and the lesson participants have learned is quite useful, and on the basis of that they will be able to build further. They will be able to progress further with the knowledge they have acquired. Number one, and number two is that they have acquired this knowledge in a newer platform, that is on online mode. So that has also helped them to encourage themselves that how to go ahead with online mode and how to deliver through online mode. I think the different topics you have covered on this intelligent subject of intelligent computing were really intelligent as well as interesting. So I also thank all the participants for taking some time from their valuable times to join this kind of FDP program. Obviously, they have benefited from this program. As organizers, I thank the Department of Computer Science and Engineering, particularly its head, the director of the School of Computational Sciences, and the other faculty members who are present and who are instrumental in organizing this FDP program. I thank you. I thank you all and hope your success also in future. I hope that in future you will organize many such programs and obviously with different levels, at different levels, so that participants can progress further after taking such program. Thank you all. Thank you very much.
Thank you very much for your kind words. And in future, currently we are also getting, and in future also in every aspect of these academic activities, we need your support. Thank you. So I welcome Dr. Somdatta Chakraborty, the Director, Internal Quality Assurance Cell of our university, to say a few words. Welcome, ma'am.
Thank you. Thank you for inviting me. Very good afternoon to everybody, to all the members in the panel and to all the participants. Today is the final day of the program on intelligent computing, and I'm sure it was really a very good teaching learning session to the cusp of information and excellence. All the speakers are doyens in their field, and their deliberations have enriched us in all possible ways. Now, one of the prime objectives of IQAC is improvement of academic performance of the institution as a quality enhancement initiative. And these kind of events are indeed a great platform to hone the skills of our faculty members. So not only that, if a repository of all these sessions are made available to the students also, which I think is available in YouTube, they will also be very highly benefited by listening to the deliberations of the learned experts. Now, I would like to specifically say one or 2 points which maybe all of us in the university can follow, and many of us follow also. In some of the workshops that have been organized before, as in some of the workshops, we may try to work on problems and small projects in workshops so that the participants can get a practical experience of the things they learn. I remember last year in a workshop, small projects were assigned to participants who had formed small groups, and they were given time to work on it. And even after the workshop ended, they were given time, and they were asked to present, and the best project won a prize. I think it was on machine learning, if I remember correctly. So we can have more hands-on sessions, hands-on training sessions, and project-based demonstrations on the latest cutting-edge technologies in these workshops as well. And secondly, I also feel that these FDPs, or the FDPs of the present times, should expand their focus and diversity by encouraging collaborative and partnered events with the industry and other expert groups in the relevant field. So this would increase the learning zone, and it will help keep abreast with the latest demands of the time. So collaborative workshops and training sessions would be highly beneficial, I feel. And as we have been organizing so many workshops and so many webinars over the last 4 to 5 months, so maybe our university can have a separate training center also that will conduct such programs on a regular and continuous basis. So which may be a source of revenue of the university as well. So in all, I'm sure that it has been a very fulfilling experience for all the learners, and will be able to take back something on which they can work on. So thank you very much for giving me an opportunity to speak. Thank you.
Thank you for your suggestions, and we will try to improvise as suggested by our Honorable Vice Chancellor, sir, that this should be a sustainable learning in the form of phase 1, phase 2, or series 1, series 2. So maybe if we will be organizing the series 2, and there we will be incorporating your valuable suggestions. Thank you very much, ma'am. Please remain with us. Now we welcome Professor Devashish De, professor of our department, and also director, School of Computational Science, to say few words.
Hello. Good afternoon. I think we already a 5 days long event, and we have seen a lot of 5 speakers from various fields. Especially, I personally enjoyed the first lecture by the TCS person. I think she's a friend of Suparna, right? Suparna. And he explained a very interesting thing, that he has not only given lecture, he has also demonstrated how to develop the mobility models of drone based, and also he has mentioned about Burj Khalifa, that competition, how they have gone through the mission mode program. So I believe that these workshops, what everyone is talking about, sustainable. So I just want to add a line that it can be inspired from the first lecture. It can be a mission mode, sustainable mode, means FDP. That means we can have some target, then only we can achieve it. So instead of going from random or haphazard, we can go for it, and I think that is a key source of success. So I must congratulate the team of organizing team, all the Department of Computer Science, IT, those who are organizing these kinds of events throughout for our students. And especially I like to thank Shumdata madam. He has mentioned about the projects and something should come out of it, right? Without the output, nothing is just like like a certificate. Certificate has no value if no output is coming. Even a few minutes before, Shagatam has mentioned that we can work together in a team. So I believe that we'll work in a team, and the group which is formed, the 87 members I can see, we can work in a team. We can make our university bigger and better. Inform that I like to inform that our MTech admission started, BTech admission started. Those who are interested in BTech, MTech, and PhD admission, they can join our university, and they can circulate because admission process is on. So you'll be having a wonderful opportunity to interact with the experts from the industry as well as from the leading scientists, those who are present even today. So by this way, you can enhance your life. So what the members who are present here, I believe just not like an invisible member, you'll be the visible member, and you'll be joining us in our team, and make this university successful, and our programs, our missions, and our hard work. I've seen that Suparna and Sriparna and everyone, those who are working very hard for this workshop, and within a very short span of time, they're organizing it. And for your information, TechEve is not the last month. We'll be having next year also. So TechEve is just a starting point. Not only TechEve, there are lots of funds are available. So if you want, fund is not a barrier. So we'll work together. I think you will take the feedback from the participants directly, so that we can make it bigger and better, and in a more mission mode, successful manner. Thank you.
Thank you very much for your valuable words. And we had I want to share that we have invited Honorable Vice Chancellor Sir IUST, Jammu and Kashmir, and TechEve Coordinator of IUST. The Honorable Vice Chancellor Sir of IUST was kind enough to join us in the inaugural session, but due to some urgent meeting they have, so both of them are not able to join us. But still, we extend our heartfelt thanks to them for being associated with the TechEve team in terms of training activities or mentor-mentee relationship or whatever. And we are very much thankful, and we are expecting to welcome the TechEve coordinator, Dr. Debashish Giri, but due to some other works or any problem, maybe we are not able to welcome him here. And we are very much thankful that we have all the organizing committee member of our Department of CSE have joined us in this valedictory session. Now I would invite Dr. Sriparna Saha, the program co-coordinator and assistant professor of our department, to extend vote of thanks.
Yeah, thank you, Dr. Bishas. As all of you already know that this 5-day long FDP is organized in association with Islamic University of Science and Technology, Jammu and Kashmir, India, and funded by TechUp 3. The theme of the program is on intelligent computing. Started from 11th September 2020 to 15th September 2020, that is today. On each of the 5 days, we were privileged to have 5 different eminent speakers with us. Today, on the eve of National Engineers Day, we are going to conclude the FDP with vote of thanks to all the stakeholders who have directly or indirectly gave us the opportunity to organize this. This event would not have been possible without the constant support and motivation from our Honorable Vice Chancellor Sir Professor Dr. Shoikat Moitro, who is backbone of our university. He always inspired us to organize such events where thoughtful ideas can be exchanged and collaboration could be possible. Thank you, sir. As this event is a part of the twinning activity under TechUp 3 and it would not be successful without the help from iOS. Next, I would like to thank Professor Dr. Mustaq Siddiqui, Honorable Vice Chancellor Sir of IOST Jammu and Kashmir to be at this particular event. Next, we would like to thank our extremely helpful Registrar Sir Dr. Partha Pratim Lahiri. The support we get from him not only during this particular organization of FDP, but all through our mundane activities is noteworthy in itself. Thank you, sir. This program has been funded by TechUp 3 and the smooth operation of this event is purely dependent on that. On behalf of all the organizing members of this FDP, we would like to thank the TechUp team of both the institutes. Dr. Debashish Giri and his whole team from TechUp 3 of MAKAUT, West Bengal has given us immense help throughout the whole organization of this FDP. From IOST, Professor A.H. Moon, Dean and TechUp coordinator and his team given their constant support also. On this valedictory session, we would like to give our sincere gratitude to our IQAC director, Dr. Somdatta Chakraborty, who is also the head of Information Technology Department of our university. Handling of financial aspects of any organization plays a pivotal role for deciding the success of that place. These have been carefully handled by our finance officer, Dr. Otri Bhomik sir. The help we got from the information scientist, Mr. Mohammad Aftabdur, is quite noteworthy. As you know, each and every day, the event is being streamed in the YouTube from the very start. Also, from making brochures to collecting feedback forms to processing all the data generated is quite a lot of work. All of that is handled by our webinar team relentlessly. Thanks to Prem Kumar and his webinar team for their behind the scene effort. Office of the Vice Chancellor Sir for publishing the brochures in the university website, WhatsApp groups, Facebook page, etc. Thank you to them also. We have started to organize this event on Monday, 7th September 2019. We got very little amount of time to arrange. Then also in the short notice, the eminent academicians managed their time to deliver their speeches for 5 consequent days. We are honored to have all of you with us. We got enlightened to listen to 5 distinct topics on 5 completely different application areas of artificial intelligence and machine learning. Along with us, we have got tremendous support from all of the faculty members of CSE department, especially our Director of School of Computational Sciences, Professor Dr. Debashish De, also the General Chair of this event. We are happy to express our gratitude to the other General Chair of this program, Professor Dr. Sriyankar Acharya. Last, but certainly not the least, the success of this event is primarily dependent of the attendees. Without your efforts, without your help, this total effort of organizing this FDP would have been meaningless. The flyer of that event has published on 9 September 2020 at around 12:30 p.m. and the last date of registration was on 11 September 2020 at 9 a.m. Within this short notice of less than 2 days, we got more than 200 participants registered for this event. So thank you to you too. Over to you, ma'am, Dr. Bishwas.
Thank you. And it's my turn to exert heartfelt thanks to Dr. Sriporna Saha, who is relentlessly working from the very beginning inception of this project, I can rather say. And because each project has some management part, everything doesn't goes with the schedule. There is some back management, there is some front on stage management, and we are having basically just hand holding during last 5 days to the best of our effort to make it successful. Thank you very much. I would just share the screen to present only the feedback that Professor they were saying that what is the feedback that we have received. I'm just sharing the screen. Please stay with us for 1 or 2 more minutes. Is my screen visible?
Yes, ma'am.
Yes.
Yeah, so we got 148 responses. This is day 2, and the three sections are there. Blue one is moderate, the reddish one is good, and the orange one is the very good. And we have got 60.8% on very good, and 35.1% on good, and moderate is rest, that is maybe how much 95, 96, 4%. So similarly for other days also it is just 1% or 2% this side or that side, maybe that varies on the topic or whatever, maybe on our coordination, I'm not sure what are the parameters based on which the participants has rated us or rated rather the session. So but they have enjoyed and liked, and that was also reflected. Maybe we will share all these informations as a fact file or fact sheet of this webinar, and that we had huge interactions in each and every session. That also reflects the fact that the participants have enjoyed a lot. So here I am sharing the stop sharing. Is it stopped,
No.
Prem Kumar?
No, ma'am.
Is screen sharing stopped? No?
Yeah, it's not
Yes,
stopped.
Okay. Okay, so we will maybe releasing a fact sheet or a fact file of our webinar of this FDP. We are also preparing, and we will share with all. Thank you very much for all the distinguished guests for being with us in spite of your busy schedule and other time-bound responsibilities. We got immense direction from all of you that we will incorporate and improvise in next series. Thanks to all the participants. Please complete the formalities, that is the quiz and feedback and all that. And the webinar team will email you your participation certificate. Please remain with us for not now, but for next program, if we will be organizing on this topic, maybe a series on advanced levels. And as suggested, maybe some project work, some hands-on, we will be trying to organize if we have some time, significant time before that. So thank you all. Have a good day.
A small announcement: quiz and feedback link has been already shared in the chat box. Please do the needful, and thank you. Yes, ma'am.
Thanks to everyone.
Thank you.
So shall we end the session, or webinar team will announce anything to the participants?
No, ma'am, the certificates will be mailed to each participant.
Okay.
So it is mandatory to give the quiz and feedback for today's session.
It
Yes.
will be mailed or the just a small
It will be
clarification?
mailed, ma'am.
Mailed,
So
everyone.
it is important to give the quiz and feedback for today. Thank you, ma'am.
Thank you
So with your
all.
kind
Yeah.
permission, ma'am, can we close the session, sir? Ma'am?
Yes.
Yes. Yes.
Thank you.
Thank you. Thank you all.